Yeah, welcome back. Welcome back. Welcome back. I think now it's fine. I like the comments. Just chat with me. Oh, thank you. Thank you. Please just chat there. I'll be able to see how to fix the problem. I'm grateful that Kapaita can see. Let the other students come. Please just shift and come. We're already here. Oh, good. It's better now. Oh, good. Perfect. I'm waiting for us to meet the 40. Good. Thank you. Thank you. Just chat. Just chat so that I can know the challenges and know how to fix it. So we are talking about lactose. And if you're told to draw the lactose, the first monosaccharide component has to be agalactose. And you can see the way galactose is at carbon atom number 3 and number 4. Oh, thank you so much. Thank you so much. Keep on chatting and liking, and we'll be able to move together to make it work. We shall pass. With all the sacrifices and all the challenges, we shall pass. So we need to put an effort. So we are saying, thank you so much. Just keep on liking and chatting, because from the chats, I know the challenges, and we also appreciate the comments and compliments and the complaints. We'll be able to fix it. Nobody's perfect, so we can fix it. Thank you so much. Now I'm saying for you to draw lactose, I will just know exactly from the first monosaccharide component that it is lactose if it is agalactose as the first component. So you can see the monosaccharide component, you have to mention that we have beta D galactose for you to get the half a mark, beta D glucose to get the half a mark, so that for the monosaccharide components, you are going to get 1 mark. Then you have to mention the beta 1,4 glycosidic bond. You'll get another mark. But for that structure, you have to score the 2 marks. So I'll check on the first monosaccharide component, it has to be galactose. If I see that it's not galactose there, then everything is wrong. However, you might mention the correct monosaccharide component, so you will get marks for that. You'll get marks for the correct glycosidic bond. But if the structure, the first monosaccharide component is not galactose, I'm not going to give you any mark. So there is a question where we are going to discuss the disaccharides. That's why I'm following the questions the way they are, such that in the essays, we'll be able to discuss all these in length or in a detailed manner. Question number 2 says, define epimass and give structures of 2 monosaccharides to support your definition. So you'll be able to see the videos after this, maybe after 1 hour, you can be able to go back and check or listen to the videos for revision before Friday. But the question number 2 talks about epimass. I say define and give structures. So you have to define epimass. Remember the epimass, they are of the same functional group. Yes, hi. So they are of the same functional group. Whitney, thank you. If it's clear, I really appreciate that the students can understand. Now, if you talk about the epimass, I'm going to write each of these questions on the board. I'm going to draw, so don't worry. I'm still explaining. If you look at the structures of those epimass, they are of the same functional group. For the ketosis, they are also epimass. We have ribulose, and we also have xylulose. For the aldoses, we also have epimass, where we talked about glucose and galactose, glucose and mannose. So if you look at epimass, they are of the same functional group. If they are ketoses, they are ketosis. If aldoses, they are aldoses. But they have a change. There is a change in a specific carbon atom, which is not the carbon carrying the functional group. So in this case, I'm talking about give structures of 2. That is why I say 2, because 1 mark will go for definition. The other mark, the second mark will go for one of the monosaccharide. For example, here, if you give me glucose, because glucose has to be the reference point. If you give me glucose and mannose or glucose and galactose. So one mark, the second mark, sorry, will go for glucose. The third mark will go for galactose. And then the other mark will go for you to explain to me at what carbon are they epimers. That's how simple it is. So let's see. After defining that they are of the same functional group, yes, but there is a change at a specific carbon atom, which is not the carbonyl carbon. Put it like this. We are talking about glucose. We said monosaccharides, the number of carbon atoms in the main skeleton. For D-glucose, for that matter, it means you are talking about D-glucose and D-mannose, D-glucose and D-galactose. If it is L-glucose, talk about L-glucose and L-mannose. Don't talk about D and the other one, you draw L. So D-glucose at carbon atom number 3, OH to the left, number 2, number 4, and number 5. That is D-glucose. But then we can start with D-galactose. D-galactose, because I've said 2 monosaccharides. I didn't say all of them. They are all, you can see, they are both from the same functional group. 1, 2, 3, 4, 5, 6. But then galactose, D, for that matter, at carbon atom number 4 and number 3, they are both to the left. So that is D-glucose and D-galactose. So what we are saying here is they are both aldoses, but there is a change at a specific carbon atom, which is not the carbon carrying the functional group. The functional group is at carbon atom number 1. The change here is on galactose at carbon atom number 4. And that is why we are saying D-galactose is an epimer of D-glucose. The reference point is glucose. D-galactose is an epimer of D-glucose at carbon atom number 4. Just by explaining that, you get the last 1 mark. So you can draw these two, or you can draw glucose and mannose. You can draw glucose and galactose the way it is, and glucose and mannose. So if you talk about an epimer pair, I said if you talk about an epimer pair, the glucose has to be there. It's either glucose and galactose or glucose and mannose. So mannose, D for that matter, at carbon atom number 2 and number 3. The carbon atom number 2 and number 3, that is where the carbon change. There is a change at a specific carbon, which is not the carbonyl carbon. So you talk about D-mannose being an epimer of D-glucose at carbon atom number 2. So you either give this structure, these 2 monosaccharide structures, or you can give glucose and galactose, the first one which I drew. So you talk about they are epimers at carbon atom number 2, meaning, of course, you have to draw. My exam is drawing, and that's why we are learning the structures. It is a must we draw. Agnes, we don't have an scapegoat here. We have to draw. I'm sorry. That's the way I can put it. We need the structures because you have to understand those structures as much as they are the building blocks of those polymers or of those carbohydrates. We have to know the structures. So, that one aside, Agnes. But you'll be able to understand them. And I told you don't cram. If you cram, my friend, you will see smoke without fire. If something is just twisted a little bit, you'll go kaput. You won't understand anything. So just try to understand how the structures come about, Agnes, if you be in class. So first, you have to understand the number of carbons for those monosaccharides, the functional group, if you are there when you are teaching naming of monosaccharides, and then you have to know the linear form for you to understand the cyclic form. So it's a process. It has to start from here, then you end to the other point. So we are talking about epimers, either mannose and glucose or galactose and glucose. So you say that D-mannose is an epimer of glucose at carbon atom number 2. That is where the last mark will come in. So it's 4 marks. Defining 1 mark, glucose 1 mark, mannose 1 mark, stating that which carbon they are epimers, another mark. Question number 3 says, it is still epimers? I think that one was not supposed to be there because it's repeated. Question number 4. Define pyranoses and furanoses and structural example to support the definition. Agnes, if you see my questions, they always ask for structures. So that is the secret of passing my exams. I like structures. Even in metabolic pathways, I need structures. They explain something in a simpler way, in a simpler manner, than writing an essay about something, you know. D-glucose is, D-mannose is an epimer of D-glucose. No, it doesn't look more like scientists. Eh? So the structures support whatever, brief, but then with the structures, somebody can easily tell what you mean. So question number 4 talks about defining pyranoses and the furanoses and the structural example to support your definition. Can D-glucose be an epimer of D-mannose at carbon atom number 3? No. Nasra? Good. When you draw it, self-explanatory. Thank you. Farah is saying something, is supporting. And Nasra, why would mannose and glucose? Glucose is not an epimer of nobody. It's not an epimer of anyone. The thing is, if you look at the structure of mannose and glucose, at carbon atom number 3, they are similar. But that is not what we are looking at. Because if you look at the definition of epimers, there is a difference. They differ. That one stands tall. They differ at a specific carbon, which is not the carbonyl carbon. Nasra, is you I'm answering? They differ. That is what we defined in class. They differ at what? A specific carbon, which is not the carbonyl carbon. So if you look at glucose and mannose, where the difference coming is only at carbon atom number 2. So glucose cannot be an epimer of anybody. Glucose is the reference point. It is either mannose being an epimer of glucose at carbon atom number 2 or galactose being an epimer of glucose at carbon atom number 4. Because if you look at the structures of mannose and glucose, everything is the same, only at carbon atom number 2. You look at the structure of galactose and glucose, everything is the same, except carbon atom number 4. So that is the difference we're talking much about. You get? Correct. So we are talking about pyranoses. I'll be able to read the charts as I also proceed. So if something is itching, just chat there. As long as it relates with whatever we are doing, we'll be able to answer. Don't worry. So don't keep quiet. Define pyranoses and furanoses. You could remember the simpler definition. Pyranose is a 6-membered ring. Furanose is a 5-membered ring. So for the furanoses, we saw that fructose, since it has a keto group at carbon atom number 2, fructose And the pentoses were going to form a furanose, a 5-membered ring. And that's what we said. When the OH at carbon atom number 5 and the functional group on the aldoses already formed the hemiacetal, it was resulting in a 6-membered ring called pyranose. When the OH at carbon atom number 5 and the functional group for the ketoses at carbon atom number 2 already formed the ketal, that covalent bond, definitely it was resulting into a 5-membered ring called furanose. So pyranose is a 6-membered ring, and you have to draw. I said, don't omit that hemiacetal or hemiketal. So don't make the 6-membered ring. The pyranose will look like this. The pyranose will look like this. The 6-membered ring. So this one has to be there. When you ask about the hemiacetal, you will mention that this is hemiacetal. But in this case, the whole figure is a pyranose. Or you can draw the structure of a beta D, galactose beta, alpha D, glucose. Still, I'll give you a mark. But even if you draw for me like this, I'll give you a mark. And then furanose looks like this. That is furanose. Or you can draw the beta L fructose, if you like, the alpha, you'll still get a point. But then, even by drawing for me those ones and defining, imagine those structures, 1, 1, and then defining pyranose and furanose, 1, 1. That's how simple it is, getting the concept. And we are saying, with reference to relevant structures, distinguish the following: a ketotriose and a ketohexose. So the example of a ketotriose, remember the table which I drew after I had introduced naming of monosaccharides, I can clearly remember, where we had the functional group and the number of carbon atoms, the main skeleton. That is what they're asking there. Because in this case, you can find that we are trying to test naming of monosaccharides, the criteria, based on the functional group and the number of carbon atoms. So you talk about a ketotriose. It is a keto, meaning the functional group is a ketose. What we are talking much about here is dihydroxyacetone. 3 carbon atoms, the second carbon having a keto group. The first one is always CH2OH. So it is dihydroxyacetone. Then here, the ketohexose, 6 carbon atoms, that is the hexose coming in, 1, 2, 3, 4, 5. And then the 6th one, or the 3rd one, or the 4th one will always be CH2OH, depending on the number of carbons we're talking much about. The first one is CH2OH. The second one where the keto group is. So just draw. You can draw D fructose or even L. It will still make sense. That one is D fructose. So it means that is a ketohexose. Hexose means 6 carbon atoms. Keto means the functional group. It is a ketose. Ketotriose, 3 carbons down the line. A keto group at the second carbon atom. Simple. Agnes, we can't escape the structures. I'm sorry, my dear. But you just have to enter. I only need 50 marks for the pass. And then I'll be fine. So we have to master. I don't say cram. Cram is a very big word. We have to master the structures, how they come about. And these structures, we've walked step by step for us to understand them. So based on the naming of monosaccharides, number of carbon atoms, the main skeleton, as well as the functional group. Then we talk about cysteine and serine. Remember, we already covered water. We already covered buffers. We already covered the carbohydrates. We already covered amino acids and their structures. So the questions relate to whatever we already covered. Yes, Nasra is asking something. Can D-glucose be epimer? Oh no, Nasra. Nasra, why are you disturbing our peace? Sorry for asking. Is it Nasra again, or I'm saying it in a bad way? From the comments, I can see Nasra again asking the same question. Or did I not? Did I miss something? Maybe I don't see the comments. Nasra, I hope you didn't resend, because I'm reading the comments, but then I'm seeing the latest one which you sent. Okay, let me assume it's not, because I can also see. Okay, sorry. I think I just saw it. It was bringing itself. Sorry for that. But you heard what I explained? Okay, thank you. Now, we are going to question number B of 5, which says, with reference to relevant structures. I know we did amino acid on Friday, yesterday, but just to refresh our minds, and even for the few days which are coming, you'll be able to master the structures. So we have cysteine and serine. Cysteine was falling under the sulfur containing. So the main idea of this question, can the student remember to draw the amino acid structure? Remember, there was the general formula for the amino acid, the carboxyl terminal end, the amino terminal end, the alpha carbon, the hydrogen up there. And then we talked about the R side chain, bringing the variability in the physical and chemical properties of those amino acids. So we saw that cysteine falls under the class of the sulfur containing. And bearing in mind, I said, for all these amino acids, for you to draw correctly the structures, we have to bear in mind the periodic table is still working. Even if we are from I think I was from the secondary school, like 2 decades. It's been a long time. But still, the mind has to be fresh with the periodic table, because we are going to look at the atomic number. If you look at the configuration based on the atomic number, for the sulfurs, we already talked much about it having atomic number 16. So the configuration going to 2 to 8 to 6, for stability, we need 2 electrons. So that's why you can see around the sulfurs, you see those 2 bonds around it. Then the nitrogen, we already know the atomic number being 7. And that's what I was saying. So we have to balance. And then serine was falling under the alcohol containing. So that is very easy. I said we just have to put a little bit effort, and then it is going to work. Now, the cysteine, if you saw cysteine yesterday, we said there is the carboxyl terminal end, amino terminal end, hydrogen here. Cysteine will look like this. Let me highlight it in black so that the students can see the difference on the R side chain, CH2SH. That is the R side chain, which brings about the variability of those amino acids. But the R side chain is the one which determines the physical and chemical properties of those amino acids. Then serine was hydrophilic. It looked like this. That is serine. Very simple. Don't complicate life. The presence of CH2OH. That is the difference between the two. Can you see? Yes. Let me put it nicely. That's it. So just by drawing those structures, each one of them 1 mark. The first one was 1 mark, 1 mark. Question number 6 says, I think still we are drawing. We are drawing the amino acids. Question number 6 says, aspartate and lysine. Something is popping on my screen, and I don't want disturbance because we've struggled for 20 minutes to make it show. Yes, it is gone. So we are saying aspartate and lysine are 2 different amino acids classified into 2 different classes based on their R side chain or R group. Mention the group, imagine, and structurally differentiate the two. I don't need you to explain anything. If I say structurally differentiate, don't go and still write stories. You know, if you look at the structure of aspartate, it looks like it has one CH2 and COOH, and you know, if you look at lysine, mention for me the class. Aspartate, acidic. Lysine, basic. 1 mark. Structure of aspartate, go straight to the structures, the 3rd mark. Give me the structure of lysine, the 4th mark. You get all your marks. I always give all my marks. I don't go back with them. Sometimes a student scores a 67 out of 70, and you can't deny the student the mark because they have written the correct thing. Even if you look for the half mark, you will not get. Yes. So, if you look at aspartate, aspartate is acidic. 1 mark. Lysine is basic. 2nd mark. Aspartate looks like this. For all the 20 amino acids, we agreed that the structure, that structure is the same. They are going to differ only on the R side chain. They are just going to differ only on the R side chain. So if you look at acidic, it's also known as aspartic acid. We already saw yesterday that they fall under acidic amino acids, that is aspartate. And then lysine, you will do like this. 4 of them. The presence of the amine group will give it a basic property. Imagine you get all the 4 marks. Clearly, you just been told, just go straight to the point. Don't go round and round. Basic amino acid, acidic amino acid. Draw the structure. Go to the next question. And I said our cut is 70 marks. For the ones who did not get it, 70. Our cut 2 is the one which will be 10 marks. So we just have to work hard for the cut 1 because it's going to hold a lot of weight. Yes. So the question number 7. We already started with what? Peptide. Yesterday, we looked at the peptide bond. And I mentioned, and I'm still mentioning, and I'm still repeating, that if you talk about a tripeptide, let's start with a dipeptide. If you talk about a dipeptide, a tripeptide, a tetrapeptide, a pentapeptide, a hexapeptide, it is based on the number of amino acids involved in the formation of the peptide bond. I repeat. The name of the peptide do not come from the number of peptide bonds formed. It comes from the number of amino acids which are involved in the formation of the peptide bond. So if you talk about dipeptide, 2 amino acids are involved. Tripeptide, 3 amino acids are involved. Tetrapeptide, 4 amino acids are involved. Pentapeptide, 5 amino acids are involved. And at the time a peptide bond is forming, a molecule of water is released. So it means for a dipeptide, 1 molecule of water. A pentapeptide, 4 molecules of water. Let's go to the question now. We are talking about a tetrapeptide called phase. And I told you in my short answered questions, I'm going to test if the student can draw the amino acid correctly, draw the correct R side chain. Do they know the 1-letter code? Which R side chain, which class do the amino acid belong to? Can they draw a peptide bond? Simple. That question is testing a lot of things there. So in my short answer, it is rare if I said for you to draw for me straight, acidic, basic, but I test using the peptide bond. Yes. So, you know, phase should be 5 marks. In fact, lineage should be 7 marks, to be precise. And I told you yesterday, until a student was laughing, hey, madam, I told you each of those amino acid will score a mark. The peptide bond will come with half a mark. And then the number of water molecules will come with another half. Because the effort is on identifying the correct structure based on one letter code of this amino acid. That one you've really worked hard to find it correctly. So we are doing phase. We are doing phase. I told you, draw each of those amino acids separately or independently, if that is the correct one. Now, let's start with our phenylalanine. That is phenylalanine. Phenylalanine. The phenylalanine was falling under aromatic. You could remember where we had the benzene ring. Phenylalanine was looking like this. That was phenylalanine, whatever we drew yesterday. Alanine was falling under aliphatic. The presence of what? Methyl groups makes them to be hydrophobic. I like using this one. Let me use another color on the R side chain to make it clear to the students so that we can clearly see. Let me start with my alanine. I come here. That is phenylalanine. This one is cysteine, which we just drew some minutes back. Draw each one of them. Draw each. That is the time you have. You don't have any other time. Give it all so that when you leave the cat room or the exam room, you feel satisfied that you've done your best. Not that you live there when you are doubting yourself. You're already doubting Thomas and you're the one who wrote the exam. I'm not sure whether I'm going to pass. And then you start saying, Madam, be fair in marking. That is the word which I hate of all. Because after me doing my part, and then you come and tell me, Madam, be fair in marking. Nothing like fairness here. We have to get the point right. So if you look at that, that's why we are revising, so that we can get right whatever you don't get. If you look at that, I'll just try to zoom, not zooming, but putting my camera to focus on each of the amino acids. Look at phenylalanine, that will be 1 mark. And that's why the 5 marks come in. 1 mark for the structure of each of the amino acid. So you can see alanine is having a methyl group, it's aliphatic. Then you have the sulfur containing, the cysteine, and then the other one is glutamate, the acidic amino acid. They're in the same class as aspartate. Some books talk about glutamic acid. It's the same one. Now, if you look at this 4 amino acid, we mentioned yesterday in class that the carboxyl terminal end of phenylalanine is going to bind with the amino terminal end of alanine. And at that point, a molecule of water will be released. Carboxyl terminal end of alanine, amino terminal end of cysteine, another water molecule will be released. Carboxyl terminal end of cysteine, amino terminal end of glutamate, another water molecule is released. Such that at the end of it, we are going to have 3 of the water molecules. For the 3 water molecules, you will get half a mark. At this point, you shall have scored 1, 2, 3, 4. 4.5. The remaining half comes here. The remaining half is for the peptide bond. It doesn't cost much because you've already struggled and drew the correct structures of this amino acid. Somebody will say, hey, madam, that one is too small now. Here, I'm just testing if you can draw the correct peptide bond. You know what a peptide bond is. Most energy goes with the correct structure of the amino acid. Carboxyl terminal end. Please, if you have to draw the peptide bond, do it like this. This horizontal part makes sense. Because if you put it here, or here, or here or here is fine for the R side chain. The peptide bond should come in between here so that you can easily place and balance the bonds around the nitrogen and the carbon. So the carboxyl terminal end of phenylalanine, amino terminal end of alanine. I have to highlight the peptide bond in black as well as the R side chain. Draw it correctly, clearly. Somebody will see that you know what you are doing. Carboxyl terminal end. Oh, I'm on cysteine. Carboxyl terminal end of cysteine. Amino terminal end of glutamate. That is how simple it is. My water has been thrown a little bit far, but we'll bring it close so that the student will not say, Madam, even yours was that far. I just gave it a space thinking that it will reach. So this is the peptide bond. This is the peptide bond where water was released. Those are the peptides bond. Simple as that. Nothing difficult. So let us see the structure of letter E. You don't see it? That is letter E. Samuel. Letter E is glutamate, acidic amino acid. Can a peptide bond be made of like amino acid, only like AAA? AAA is always, a poly-A tail is always a stop codon, but then it is not an A only, it is TAA, but those are bases. So in the case where I talk about amino acid, I don't know whether those codon could be coding for that amino acid. So depending on how you want it, I can't set for you AAA. That is so simple. But what I want to see is, do you get the concept of a peptide bond? Can you draw the amino acid? Do you know the structural classification of those amino acids based on their R side chain? So whichever way the peptide bond you're told to draw, like the next one we are going to draw is a bit long, but we talked about one letter code being a unique identifier of those amino acids, just as your registration number. You know, even for someone who has left MKU, they will still retain that registration number. They are not going to recycle it and give another person. That is the unique identifier, such that when you come even after years, they put that your registration number in the system, all the information about the students will come. The same with the ID number now. You can't share the ID number. If it's put in the system, in the offices, wherever you go, all information about this person will come out. So that's why we talked about one letter code being a unique identifier. The secret of knowing 20 amino acids. Now what is the secret? No, we just have to study. Fahar, we just have to study. But what I can advise, don't try to read all at a go. I'm saying because maybe you start by reading today. Before we do the cut, it will be how many days? And then a day has 24 hours. So let's say today you want to do aliphatic only, because aliphatic is too wide. There are 6. You can do aliphatic today, but then do when the head is fresh, you know? The formula to remember. I'm not always good in singing, but I think there should be a formula. There should be a formula. There should be a formula. If you can sing the aliphatics and you know them by one letter chord, I still can't remember any formula. I'm not always good in storytelling and singing, but I think there should be a way. Maybe cat, ren, or whatever. Yes, but then that one I have to tell you, I still don't know the formula. What I could tell much is how we could follow the formula of acidic. We could follow the formula of phenylalanine, but only a few had unique identifiers, maybe the one letter code, which was different from the first letter. The first letter of what? The first letter of the amino acid. Most of them, almost 14, the one letter code is obvious. Only for a few. Yeah, Whitney is saying, I'm very happy I'm getting everything. Okay, I'm happy. But then Faraday, is it Fahandri? Yes, there will always be a formula. So what we can do, just read in bits. Don't wait until Thursday, then you want to read all the 20. And then I have also to set about the structures of the carbohydrates. My friend, your head will burst. I'm talking about somebody who has been reading from week 1 when you started class. So you read bit by bit, such that when you start a new one, when you start a new class of amino acid, revisit first whatever you did for the previous time. Just have an empty paper, a blank paper. Then try to recall whatever you read yesterday before you can start on the new ones. You'll realize that it is entering. And if biochemistry becomes a challenge, let it be the first thing in the morning you read when you're fresh, or when it is quiet like now, but you've already eaten supper and the brain has enough of the glucose, my friend. Don't read when you are hungry. Don't read when you are tired. You are not going to get anything. And then have a scheduled time. Don't just overread. You just read throughout, and then you take water and basin on Thursday and you put your feet. You are not going to get anything. Yeah? So it's just, everyone has a strategy. Somebody is asking a question, Gesare. So you just join any 4 amino acid to form the tetrapeptide? Correct. As long as there are 4. We can think of any. The other time I told you to think about a name, and we came out with Dan. Dan were 3 amino acid. That was a tripeptide. If you add a Y, we could talk about Danny. So it's just a matter of practicing with any of the 20 amino acid 1-letter codes. That is the essence. But then you have to know that the name of the peptide comes from the number of amino acids that are involved in bonding, not the number of peptide bonds which are forming. Daniel? Yes, I think I tried to answer. Was it Nasra? Yes. But it shall be well. If you put an effort, it can't go. It can't go to the gutters. That is not paid off. If you genuinely put an effort, the 3 months for the semester will pay. It will be payback time when we start a new semester. You'll be smiling on your portal. And now that the portal, your portal is fine. You can manage your stress at your own corner. During our time, it was just you go and see. The dean of students, you're going to get your marks. And then they write it on a paper. But nowadays, you have your portal. Nobody knows what happens there. You are the only one who knows. Whether you are managing with a lot of celebration, whether you are managing with a lot of supplementaries, no, it is your own life. Just program it well and everything will be fine. It doesn't mean that if you have supplementary, you're a failure. Who said so? No. It's only that there is something which we didn't get it right at first. And that is why we are doing it for the second time, so that we can get it right. Yes. So don't worry. An effort, if you put an effort and you sacrifice, it will never go unanswered or paid back. We are at let us do the hexapeptide. The hexapeptide. To support whatever we've written so that we can understand much. So that day when you see a tripeptide, you try to ask, now what is Madam setting now? This one we revised. That is a good thing with revision. And when my students go for exams, I'm always very confident that I've done my part. And you can easily answer any of the questions confidently. Without Mwakenya. Don't try Mwakenya. Yes. And that is why we are trying to put an effort. So we are talking about question number 8. It relates to the previous question, but now it is lineage. We are just using any of the words. I'm going to show much of my camera after I've drawn. So let us start with, this is leucine. Leucine was in the class of aliphatic, but then I said it falls under the subgroup of branched chain. So the major group is aliphatic because of the presence of the methyl groups, and it was looking like this. It was looking like this. That is how it looked like. That is how leucine looked like. And then the isoleucine was looking like this. Isoleucine was looking like this. Isoleucine was looking like this one. Isoleucine was looking like this. That was isoleucine for us, whatever we drew yesterday. The presence of the methyl groups makes them hydrophobic. Asparagine was amide of aspartate. Remember what we did yesterday? Asparagine was amide of aspartate. Asparagine was amide of aspartate. I said there is several ways how it can be drawn, but the simplest one is this one. And then alanine. Alanine was also aliphatic. We have many of aliphatics here, but it's still okay. Draw each one of them. You will get 1 mark each. Glycine was the simplest. That is what we learned. The first one which we drew, glycine, I think they're too long until our glutamate will be fixed there, but we will still draw it. I'm going to project well, focusing my camera to each of the amino acids before I can draw the peptide bond. NH2. Remember, we already drew this glutamate. We already drew glutamate. Yes. So each one of them, 1 mark. It means already 6 marks scored. But I always don't give such a huge one. You just limit. So you can see leucine, the presence of the methyl groups makes it to fall under the aliphatic, but then the subgroup branched chain. Isoleucine the same. They're in the same class as leucine. And if you look at it, you'll see it's also branched. And then you'll have asparagine, amide of aspartate. Aspartate had CH2COOH, but now we've added the amine group. So you talk about the amide of aspartate. Glycine was very simple, only hydrogen, and then glutamate is there. So for you to draw the peptide bond, I know it's going to be long until we would be able to find a space. Just the way we drew the other one, I'm going to draw. But now let me draw without mixing the colors. I'll just highlight so you can see carboxyl terminal end amino. carboxyl terminal end amino. That's where the water is released, carboxyl terminal end and amino, carboxyl and amino, carboxyl and amino. So you are going to have something like this. I'm going to draw with black. I'm going to draw with the black so that we can try to move a bit faster. That is the peptide bond, just whatever I do the other time. But now I'm not highlighting with the other color. Peptide bond. And we talk about a hexapeptide. 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 Carboxyl, amino. We are at alanine. Carboxy, amino. We are at glycine. Carboxy, amino. The last one is glutamate. But then, how many water molecules? 5 of them. Because 1, 2, 3, 4, 5. And then the peptide bond comes here. The peptide bonds come here. The peptide bond is here. The peptide bond is here. And the peptide bond. Simple as that. Why would I not give you the mark? Yes? You will tell me if you will be fine if I do and I stop at the SAQs, or I can still proceed with the essay and finish. So you will tell me. Because people can get tired. You can be talking to your own. You don't know that the students, their mind left long time ago. So you are the one to tell me. If you talk in unison that we can go as far as finish even the essays, or I can finish the essays maybe on not on a Tuesday. On a Tuesday I have a class. On a Wednesday, then we'll be able to talk about it. But for now, let me go to the other question. It talks about draw structures. You will tell me when I finish the short answer. I always don't like to go too much, but then let's see how it goes. We are at question number 9. We are talking about draw structures. Angela, we are still drawing structures, my dear. I'm sorry, we don't have any other option. Draw structures of any three monocarboxylic amino acids. Some are asleep. Ochieng. Good. Let them sleep. When they are sleeping, that is the part when I'll set. So it means I need again another person, because I'll stop at short answers. I'm not going to start on essays. I don't like to talk too much until the students lose focus, because I know we are human beings. You can get exhausted. That one is an exemption. So it's not an exemption, sorry. So we are talking about monoamino monocarboxylic. Can somebody write a chart there? Which amino acids, example of amino acids we need to draw for question number 9. Example, monoamino monocarboxylic. That is the way I can also, but I always set it in essay, because you have to draw several. Can someone say an example of that if they got what we learned yesterday? Mono, amino, mono, carboxylic. Shift the camera to the left. Can see clearly. Oh, kappa, all aliphatic, correct, Rahma? Yes, mono, good, correct. Methionine, aliphatic and aromatic, but then aromatic will exclude the tryptophan. Tryptophan has a nitrogen somewhere. So for the aliphatic, correct, because even proline has the 3 methyls, which you saw. Methionine, correct. So the point is clear. Look at the structure, the whole structure of the amino acid, correct. Serine, correct. So look at the structure of the amino acid. How many amino groups? Correct. Tyrosine, very much correct. People are awake. Let's leave the essays for another day. Correct. That's what I think as well. All aliphatic, correct. So that one can be answered correctly. If we connect it with question number 10, you are the one who is going to tell me. Correct. Glycine. Glycine is in the aliphatic, correct, Daniel Gesare. Now, I want the answer for question number 10. Diamino, dicarboxylic. Let's start with diamino, dicarboxylic. How about all alcohol containing? Wait, Rahma is asking a question. Yeah, leucine is correct. Rahma, yesterday we looked at classification of amino acids and we did 4 classifications. So if you talk about alcohol containing, we are talking about the structural classification of amino acids based on the R side chain, which we started off with, and we labeled it as A. Then we had to go to B, where we talked about the charge. Then C, where we talked about the number of amino and carboxyl group. So we are talking about the 3rd classification here. Then the 4th one was nutritional classification, Rahma. So don't mix these things up. Correct. Now that number 9 is well answered. Everyone's answer is correct. I'm looking for question number 10. Don't go to the other part. I'm still on the first part of question number 10. Draw all the diamino dicarboxylic. Diamino dicarboxylic, draw all. Correct. Murithi already said the first one, glutamine, diamino dicarboxylic. That is 1 mark. Just by drawing that glutamine, because it's 4 marks. The other one, Murithi has said the first one, glutamine. Somebody? No, Daniel, cysteine is not diamino dicarboxylic. Just look at it. Look at the structure of cysteine. So if you look at the structure of amino acids, correct, asparagine, very much correct. It's only glutamine, correct. Amides of acidic, those are diamino dicarboxylic. And then that is 2 marks. It only have glutamine and asparagine. Then the other side of the question number 10, monoamino dicarboxylic. Yes, correct, Kiprotich. It was asparagine. That was the first one. Now I need the answer for dicarboxylic monoamino. No, what did I say? Sorry. Monoamino dicarboxylic, correct. So who are those? Because in total it was 4 marks. For the structures, amides of acidic, that was the first part. Now the other part, monoamino dicarboxylic means, correct, aspartic and Murithi, give us the second one. Yes, aspartic is the aspartate. Aspartic acid is the aspartate. And which one? There are also only 2. So that's why it was 4 marks. 2 amides of acidic and correct glutamate. Very thank you, Cornelius. Aspartic acid. Correct. So simply, the question was asking for structures. The diamino dicarboxylic were amides of acidic, and then the dicarboxylic monoamino were the acidic. So each one of them correct. So all the answers there are correct. So each of those structures is going to give us 4 marks. So 1, 1, 1. Simple as that. Yes, Emmanuel, that's fine. So I'm happy. The boys and girls are active, but we are going to stop at the end of the SAQs. I always say the world is not ending today. Yes, Mumtaz, that is correct. All acidic are dicarboxylic monoamino. All the amides of acidic are dicarboxy diamino. The aliphatics, the alcohol, the sulfur containing, they fall under the monoamino monocarboxylic. Question number 11. I think there are 13 questions. I'm almost. So don't get tired. The one who is tired, I'm already stopping. Question number 11 says that define functional and stereoisomers. It means define functional isomers and stereoisomers, then you draw structures. That's how simple the question is. Draw, yeah, Faith, that is fine. Draw, define functional isomers and stereoisomers first, then you draw. If you talk about the functional isomers, I'm going to draw them on the board. If you talk about the functional isomers, they're of the same molecular formula. If they're exoses, they will be C6H12O6, but they differ in structure based on the difference in the functional group. So it means one is a ketose, the other one is an aldose. Aketose and aldose. D-fructose and D-glucose are functional isomers. Stereoisomers, they're of the same functional group, same molecular formula, but structurally, they are mirror images of one another. Oh, wait. Is there exemptions in the monoamino monocarboxylic acids? What do you mean by exemptions? I don't understand the exemptions point, but any of those amino acids with one carboxyl group, if you look at the whole structure plus the R side chain, one amino group, then that falls under that. So it means even the essays, I can talk about draw 10, because I know they can be more than 10 or they can be less than 10. But for the monoamino dicarboxy, I know there are only 2. So I'll say all. For the dicarboxy diamino, there are only 2. Lovely. Yes. So we are saying that for functional isomers, from the name, it means that the functional group differs. Oh, this is the second last question, and then I'll be able to work on the number 12, and then we'll stop. Sorry. So we are talking about functional isomers. From the name, you will know that the functional group differs. One is a keto, the other one is what? An aldo. Let me give the best one, which you already know, is D-glucose and D-glucose and D-fructose. But I'm going to draw for the dihydroxyacetone and glyceraldehyde. a ketotriose and an aldotriose. Those are functional isomers. Ketotriose, ketoaldose. Ketohexose, 3, 4, 5, 6. Ketohexose, D-glucose, or D-fructose, sorry. And aldohexose, 3, 4, 5, 6. Aldohexose and ketohexose, those are functional isomers. Simple, define, and give the structure. You can give any. As long as the functional group are different, those are functional isomers. But then, stereoisomers, simple. That one is, we are going to use this one as an example. L-glucose. See, I said for L, apart from a carbon atom number 1, number 6, 1, 2, 3, 4, 5, 6, whatever was to the left comes to the right. Whatever was to the right comes to the left. You get? So it means that D-glucose and L-glucose are stereoisomers. D-glucose and D-fructose are functional isomers. I'll stop at this point. I'll finish question number 12 when we meet on Wednesday and the essays. I can sense that the students are already sleepy and tired. It's 11 sharp. Is it sharp? No, it's almost 11. That is already an hour plus, an hour and a half. So kindly, I say thank you for coming on board for the revision. You can go through whatever we've done so far to try to recollect much of what you've read. It will be of help. Before we reach Wednesday, you can still go through the essay equations because part of them we've covered in the short answer, such that by the time we reach on Wednesday, attending to the essays, it will be easier. So, still the same time, Rahma, I like at 9. I like at 9 when it's quiet. And even my children have gone to sleep. So no disturbance. They are watching football. Okay. Okay, let them go and watch football. But tell them to concentrate on the revision. They can embark on revision after seeing whoever has won. It is still okay. Right? So you people have a nice evening and good night to all. Thank you so much and God bless.